CP2 MixEx5 Question 12. This question involves polar coordinates, which should be pretty obvious from the diagram and the fact that it says we have a polar curve, r equals 4 cos 2 theta. You don't necessarily need to recognize that 4 cos 2 theta is going to give us a nice curvy petaled shape in this particular case. All we care about is this first little bit of the curve. But it's worth thinking about when we touch each part of this curve. So the first thing I would do with this is to try to get a feel for the situation by subbing in, possibly just in my head, the extreme values of theta. At 0, we've got r equals 4 times cos 0, so that's 4. So it must be right here. And then at pi by 4, r equals 4 times cos of 2 pi by 4, so cos of pi by 2, and that gives 0. Cos of 90 is 0, so that means we've got to 0 by the time we reach pi by 4. So that's consistent with the diagram, and we can see that as theta increases, as we trace around the angle between 0 and pi by 4, just going this first 45 degrees, the r value shrinks from 4 all the way down to nothing. Now they've given us the point A, where r is 2, and we're asked to find the area. The first thing to highlight here is that although it looks like the kind of question that you might just do straightforward integration from b to the end, from b to 4, that's not going to work here because polar integration does not behave the same way as Cartesian integration. We're not just working out the area of a bunch of tiny, thin vertical rectangles. We're working out the area of a bunch of tiny, thin, sector-shaped slices, as you can see from this little picture down here. So my process is going to look something like this. First, I'll find the relevant value of theta. I need to know what theta is at the point A, and I can do that by subbing in r equals 2, and I'll just solve to find theta in the range 0 to pi by 4. There should be just one value because there's a single unique value A at which r is equal to 2. Then I'm going to find the Cartesian coordinates of A, and I'm going to double check that the values make sense. Should be positive for both x and y, because it's in the first quadrant, and the x coordinate should be somewhere between 0 and 4. That's obvious because I already know my curve goes from 4 here all the way down to 0 here. The next bits benefit from having a slightly bigger diagram, which is why I've done this. If I were to add up all of the tiny thin segment slices that I get when I integrate using polar integration, I'm going to get an area which is too big. But it's going to be too big by exactly that red triangle in here. So all I need to do is integrate between 0 and whatever theta is, and then subtract the area of that triangle. There are a few other ways to do this as well. You can integrate from 0 to pi by 4 if you like, but then you'll need to be subtracting a bit more. You'll have to take away the little extra piece, that little curvy bit between O and A that's above the straight line. So there's a few other approaches, but if you take a bit of time to draw out a nice big diagram, get a clear plan in place before you jump in, it will save you time in the long run, I promise you. So let's find the value of theta. We sub in r equals 2, and we can calculate that theta is either going to be pi by 6 or minus pi by 6, but pi by 6 is the only solution that works here. Pi by 6 is sensible, that's 30 degrees. It's consistent with the fact that we're only looking for values between 0 and pi by 4. And then I can work out the Cartesian coordinates by using r cos theta and r sin alpha for x and y. That gives me x equals root 3 and y equals 1. That also fits with the picture. It looks like a distance of root 3 or 1.7-ish is fine. In fact, that's a little less than half of 4, which is not just consistent with what I know to be true, that it's between 0 and 4, but also with what it appears to be on the diagram, which is a little less than halfway from the pole to the crossing point up here. And the height of 1 is also consistent. The area of the triangle, I've not even written working out here because it's basically also the solution. We do root 3 multiplied by 1 and then divide by 2 because it's a triangle. So base times height divided by 2, that's the area of the triangle. And I'm going to make sure that I go through my checklist, ticking these off as I go, so I don't forget to subtract that at the end. Now, the polar curve integral, you've got to be careful with this because we're adding up a bunch of tiny sectors. We're using the radians formula half r squared theta. But the theta value we're using is a tiny infinitesimal slice of theta. So that's the bit that becomes d theta when we take the infinite limit. And that's why we need to integrate half r squared d theta. Well, we're going from 0 to pi by 6, so I'll put those limits in as well. R is 4 cos 2 theta, so r squared is going to be 16 cos squared 2 theta. And because of the half, I'll just end up with 8 cos squared 2 theta. I'm also going to make use of the double angle formula here. It might be a little confusing because we already have double angles. We've got cos squared of 2 theta. But the important thing here is not that we've got cos squared of 2 theta, it's that we've got cos squared of 2 theta. And we can replace cos squared of anything with something involving cos of 2 lots of that anything. So in this case, in the same way that cos squared of theta is equal to 1 plus cos 2 theta over 2, cos squared of 2 theta is equal to 1 plus cos 4 theta over 2. So my integral can be turned into one that does not involve the square of a trig function. Notice that because this was something all divided by 2, that's going to cancel quite nicely with the 8 and leave me with a 4 in both places. And one further nice cancellation happens when you integrate, because cos will integrate to sine, but we divide by the derivative of what's inside there. Something linear, so it's perfectly fine to do this directly with inspection or reverse chain rule, but we have to remember to divide by the 4. So that cancels out the 4 in front of the cos 4 theta. Then we sub in the values, and I'm lucky here that the first part is just theta, and the second part involves sine of something theta. So if theta is 0, both of those disappear entirely, and all I need to worry about is what happens when theta is pi by 6. So 4 theta is 2 pi by 3, and sine of 4 theta is sine of 2 pi by 3, which is root 3 over 2. So I've got my curve area, 2 pi by 3 plus root 3 over 2. The triangle area was also root 3 over 2, so I'm subtracting that, and that leaves me with 2 pi by 3. And at the end here, I'm just going to do a quick sense check to see if this is reasonable. 2 pi by 3, according to my calculator, is roughly 2.1. And if I have a look at the diagram, bear in mind the shaded part here. We already have lots of information. You might even have jotted some of it down onto your diagram. 4 at the extreme end, root 3 at B. So the width of that is going to be 4 minus root 3. That's 2 and a bit. And then the height between A and B is 1. The curve might get a bit higher than 1 in between, but probably not high enough to make a huge difference to our estimate. So although this rectangle will not necessarily be a strict upper limit, it is going to be approximately equivalent to my value. So if we multiply 4 minus root 3 by 1, we get roughly 2.3, which is pretty close to 2.1, so I'm happy that my answer is reasonable. Quick bonus section here. That bounding rectangle, I was curious to see whether this curve did actually go above 1. It turns out it does. It gets to 1.09-ish at its greatest point. But it's a little bit sophisticated to work out exactly how. It's quite nice, however, to do it using the T formulae from further pure 1. So if you're doing FP1, you can have a look at this bit and see how the T formulae gave me a quick, efficient way of working out this point. I want the maximum value of y, which is r sine theta. But r is 4 cos 2 theta, so I'm trying to find the maximum value of this. And this trig combination, a cos multiplied by a sine, but with a 2 theta and a theta, a little bit messy. So I need some product rule. I apply product rule and I get this, an even messier bit of trig. But since I only care about the maximum value, I'm going to set that equal to 0, which is equivalent when we rearrange to this. We can divide through by cos 2 theta and by cos theta, and it turns all of this into a problem involving tan. Technically, all I'm doing here when I apply my T formulae is using the tan double angle formula, but it's a nice quick one for me to remember in terms of T. So I'm going to replace tan with T, and that means I have to replace tan of 2 theta with 2t over 1 minus t squared. Take care here, normally the T corresponds to tan of a half theta in the case where 2t over 1 minus t squared is equal to tan of theta. So in this case, I've just got the doubled up version, in the same way that our cos squared of 2 theta ended up being written in terms of cos of 4 theta. So 1 equals 2 lots of tan 2 theta tan theta turns into this equation, which simplifies quite nicely into a quadratic, a nice simple quadratic that we can solve. If t squared is a fifth, t is plus or minus 1 over root 5. And when we solve, there is only one solution in the valid range, and that's about 0.42 radians, somewhere between pi by 7 and pi by 8. and we can then sub that back into the original to work out the y coordinate, 1.089. So it turns out the bounding box I was describing is just a little bit too low, even though ultimately the area of that rectangle is still going to be bigger because of the curve we've got here.